Hello and welcome everyone to the first video of my mini course. And in this mini course, we'll talk about, as I mentioned in the abstract, about sharp upper bounds for Laplace eigenvalues and connection of this problem with harmonic maps and minimal surfaces. So the first video will be very basic. I'll just introduce the Laplacian eigenvalues and slightly outline the connection to minimal surfaces harmonic maps. Then in the next video, I will talk about some recent results. And then the later two videos will be dedicated to some more in-depth discussion on those recent results. Okay, so let's first set up the problem. First thing I want to define Laplacian eigenvalues. So we'll be working mainly on the surface. You can say a lot of things about a similar problem on the high dimensional manifold, but this is much less developed area. So we're going to keep ourselves to surfaces where much more is known. So we consider closed surface, which means that it's just compact, connected without boundary. And Laplace-Beltrami operator, or simply Laplacian, is an operator which is, for example, in coordinates written like this. You can also know it by name, by delta D, right? Where delta is a joint operator to a differential. If you haven't seen any of those definitions, there's nothing to worry about. Basically, there's some way to extend the usual Laplacian Rn to arbitrary manifold, and it's natural canonical way. So it's canonical operator associated to any Riemannian manifold. So the only thing to keep in mind here is that I have this minus in front. So if G here is just a flat metric, then I get minus signs of second derivatives. You'll see in a second why minus, or why do I put minus here. And we solve for eigenvalues, right? So basically think of this delta as a usual symmetric matrix on an infinite dimensional space. And then you solve this problem, which means that you just look for eigenvectors, right? But now they're called eigenfunctions because you're solving for functions, right? So we're looking for eigenfunctions of a Laplacian. And it turns out that the lambdas, the eigenvalues, so the lambdas for which solution of such equation exists, non-trivial solution exists, they form a sequence like this. And the first eigenvalue, which we call lambda 0, so it's a first eigenvalue, but it's actually 0th eigenvalue because it's always there. It has a multiplicity 1, and it corresponds to constants, right? So constants are the only harmonic functions on the closed manifold. And all the others are written with multiplicity, right? So if I have, if my eigenspace, if my eigenvectors form like three-dimensional space, I'll repeat lambda 1 3 times in the sequence. And then the sequence will be going to plus infinity. And moreover, the corresponding eigenfunctions form a complete basis of L2. Right, so those are basic properties of those eigenvalues. Let's look at one example where you can compute them explicitly. One of the examples where you can compute them explicitly. So look at the torus, flat torus. So what you need to do is that you take R2, usual plane, and you take the lattice generated by two vectors, right? And your fundamental domain of this lattice will be this parallelogram. And what you do, you identify this side with this side and that side with that side. Right? You get nice torus. The critical feature here is that for different A and B, you get actually different Riemannian manifolds. And we'll see in a second why. Right? We'll compute their spectra, the eigenvalues, and we'll see that they're different for different A and B. All right, so how do you find the eigenvalues of this? Well, you just solve this equation, right? So the point is that any function on the torus is just doubly periodic function on R2, on the plane, right? So you can look at this just as an equation on the plane with periodicity conditions like this. So how do you solve it? Well, let's first find some solutions of this equation. And the idea is that we know that a usual exponential, right, e to the power ikx, solves a similar problem in one-dimensional case, right? So second derivative of e to the power ikx is minus k squared e to the power ikx, right? So the idea is that you use exactly the same kind of functions here. So let's substitute f of xy equals this exponential, right? So xy times some vector, scalar product with some vector v, right? So if you plug it in, you'll see that the length of vector v is exactly eigenvalue lambda, right? So the functions of this form, they all solve this equation. But what about the conditions, right? So the conditions imply that this function has to be periodic. So if you plug it in, you'll see a certain condition on v. Namely, v has to have integer 2 pi times integer scalar product with any vector in the lattice gamma, right? So if you shift by a vector in the lattice gamma, this number in the power of exponential needs to change by 2 pi in order for a whole exponential to stay the same. So the v has to be in what's called dual lattice, right? So it's a lattice which is formed by vectors whose scalar product with the original lattice are integer numbers, right? And so this gives you discreteness, right? So we know that the eigenvalues have to form a discrete sequence. So this is a discrete lattice, and the lengths of vectors in that lattice give you exactly the eigenvalues. For example, in this case, for this particular choice of lattice, dual lattice will look like this, right? And you can compare different A and B and see indeed the spectra are actually different for different A and B. So those are different Riemannian manifolds, and eigenpairs of eigenvalue and eigenfunction correspond exactly to the elements of this space, right? So what we've done so far, we've just computed some of the eigenpairs. But the point now is that with some elementary Fourier analysis, you can show that this is actually a complete basis, right? So there cannot be any other eigenpairs in this space, right? And indeed, you see it's a discrete sequence going to infinity, and they're different for different A and B, right? So the basic way to see eigenvalues as an invariant of Riemannian manifold. Okay, so what is the other significance? What is the why do people care about eigenvalue? Right. For example, there's this characterization of lambda 1, which is very important in geometric analysis. So one way you can compute, for example, the first eigenvalue of the symmetric matrix, right, in Rn, is to do what's called the variational principle, right? So you consider bilinear form, which is just, so if A is just a matrix, right, symmetric matrix, you can find the first eigenvalue, the smallest eigenvalue. We call it lambda 0 because for us lambda 0 is the smallest eigenvalue, as a minimum of AVV divided by VV, right? So this is something which is covered in linear algebra course. All right, so you can find the eigenvalues from the corresponding bilinear form by minimizing the bilinear form. The similar characterization works for Laplacian on infinite dimensional space, right? So for self-adjoint operators on infinite dimensional space, and for example, for lambda 1, there's this characterization, right? So you need to ask something about your function u, namely you ask it for it to be orthogonal to the first eigenspace, right? So the first eigenspace is just functions, it's just constant functions. So you ask for it to be orthogonal to constant functions, which means that the integral is 0, right? So lambda 1 is infimum of this ratio. So the integral of differential squared, L2 norm of differential, divided by L2 norm of the function. So you can actually recognize now what lambda 1 is from this, right? So lambda 1 is actually, if you rearrange the terms, so you know that lambda 1 is always bigger or equal for any function with 0 average than this ratio, right? So if you arrange the terms, you recognize the Poincare inequality. Oh, sorry, not this is the opposite. direction of the inequality is opposite, right? So lambda 1 is less or equal, right? So lambda 1 is infimum over all. So lambda 1 is less or equal than this over all possible functions. So if you rearrange the terms, you get the classical Poincare inequalities for functions with zero average. And so in fact, what you get is that 1 over lambda 1 is optimal constant in the Poincare inequality. All right, so this is one of many reasons why the first eigenvalue is important in geometric analysis. And the last comment is that this number, this ratio is called Rayleigh quotient, And there's similar characterization for higher eigenvalues, which also can be analogous to that for usual matrices, right? You can consider the same sort of Rayleigh quotient as here, but now you do the following in sup construction. So you look at all k+1 dimensional subspaces in H1, for example, and you take a sup of all functions in that subspace, right? And the idea is that the bottom, you need to take lowest k+1 eigenfunctions to achieve this inf, and then instead of inside the eigenspace space spanned by those eigenfunctions, you need to take the highest possible eigenfunction, right? So this is the characterization, and you can actually use this characterization to prove that the eigenvalues go to infinity, right? If you use this plus compactness of the embedding H1 to L2, you get all those properties for the spectrum that I mentioned before, right? It's discrete and it tends to plus infinity, right? If you haven't seen this before, this is a good exercise, right? So use this plus compactness of H1 to L2 to prove that the eigenvalues go to infinity. All right, so those are a quick rundown of what eigenvalues are and how to think about them. Basically, it's just like the usual matrices, but on infinite-dimensional space. So what is the problem that I'm going to be considering in these lectures? So I'm going to consider this quantity, which is called normalized eigenvalue, lambda k times the area. So the good thing about this is that in a second, we're going to optimize the eigenvalues. And when you optimize something, it's important to have something scale invariant. So if I multiply a metric by a constant, I expand the manifold, right, or I shrink the manifold, my quantity that I care about remains the same. All right, so here, if I multiply by area, this product is actually scale invariant. So eigenvalue by itself is not scale invariant, but this product is. That's why we're considering it. And we consider this normalized eigenvalue as a functional on the space of all Riemannian metrics, right? So if they fix M, fix the surface M, and allow metric to be whatever you want. And you want to optimize this quantity. It turns out that infimum is always 0. So you can always deform the metric so that the eigenvalue, any eigenvalue will go to 0. And the interesting problem is in supremum. So I will denote by big lambda k of m the supremum of all metrics of this normalized eigenvalue. And there's going to be a second quantity which is just as important as supremum in the conformal class, right? Where a conformal class is, so I fix some background metric, g, and I look at all metrics which are positive function times that metric, right? So those deformations, they don't change the angle, but they change the lengths of vectors. That's why they're called conformal, right? Conformal usually refers to something which preserves the angles. And we're going to be looking at exactly those quantities, right? And that's the main object of the lectures. And basic questions are these quantities finite? If they're finite, what is the exact value? And what are the metrics that achieve the value if they exist? Right, so those are three basic questions for any optimization problem. So let's answer the first question. What are the upper bounds? So it turns out you can prove the following upper bound. If you consider any orientable surface of genus gamma, then you have this upper bound, right? Where this square brackets, this is the integer part. Or floor function, right? Sometimes it's called a floor function. Right. So the point is that it doesn't really matter what's the value in the right-hand side for now. The point is that independently of g, whatever G is, normalized eigenvalue is bounded by this quantity. In particular, it tells you that big lambda 1 is bounded as in it's not equal to infinity, big lambda 1. You can prove the same thing for non-irreducible surfaces. You have a slightly worse constant, but the point is the same. Right? It is finite. Big lambda 1 is a finite quantity. And furthermore, for any surface of genus gamma and for any k, you can prove similar bound for the kth eigenvalue. The only downside is that it's implicit, right? So there's just some constant. You know it's bounded, but you don't know exactly what it is. But again, for our purposes, we just want to establish that lambda k is less than our quantity what we care about is less than plus infinity. And indeed, those bounds do this nicely. Right, so now we know that big lambda k is a finite number. Right, so we'd like to understand exactly what does it equal to for different values of k and different surfaces m. Right, so what is known? Let me first give you some elementary examples so that you basically to show that you get some natural answers in this problem. So for the sphere, you get that the maximum is achieved on the standard metric on the sphere, on the round metric in the unit sphere, for example. Right, and the value is 8 pi. For a projective plane, you get the usual standard metric on RP2, which is obtained from metric on S2 by antipodal projection. Right, again, very natural answer. For torus, you get a flat metric, but not just any flat metric, right? So flat metric, one of the class of the metrics that we considered before. It's a flat metric for very special lattice, which corresponds to a equilateral torus, right? So you look at the lattice, which generates equilateral triangles, and you take this one, and this gives you the value, such as this, and achieves its supermode. Right, so at the first sight, it might seem like, well, all those metrics. So what's so special about those metrics? The first sight might seem that, well, they have constant curvature. That must be why they occur here. In fact, no. And the reason why they occur is because they're connected to minimal surfaces. Right, and that's what I'm about to tell you a little bit. So what is the extremality condition? So this will be the main topic of our third video. Well, I'll explain in detail how can you obtain those conditions, right? But the basic rundown is that you take your functional, right? You want to understand what does it mean that derivative is 0, right? Just first order condition. You don't know how to find the maximizers. Well, let's find critical points first, right? And such metrics are called extremal metrics. Again, I'll talk about it in more detail in the third video. So let me just state the result that you get. So suppose we have a extremal metric for the functional, for this normalized functional, in the fixed conformal class, right? The fixed conformal class, I only allow metric to vary inside this conformal class. I take the corresponding eigenspace. It turns out that you can find a collection of functions in this eigenspace, right? It's a collection of eigenvectors with the same eigenvalue, lambda k, such that it forms the map to a unit sphere, right? So point-wise, sum of squares of eigenfunctions would be equal to 1, right? So another very strong condition, particularly it implies that eigenspace has to be multiple. For one function, it's impossible, right? So if you have just one function, sum of square, if its square equals 1, it has to be plus minus 1 constant, which is only possible for the 0th eigenvalue. So first glance, it seems like, oh, okay, that's a nice condition, but not much more than that, right? Just collection of eigenfunctions such as sum of squares is 1. In a second, I'll explain it's actually very geometrically natural condition. And so, but before doing that, let's look at the extremality condition in space of all metrics. If you look at the space of all metrics, and let's rescale our metric a little bit so that the first eigenvalue would be equal to 2. It will be clear in a second why we do this. So if you do that, again, you have the corresponding eigenspace, you have a corresponding map, right? Again, if you are extremal in the space of all metrics, of course you're extremal in the space of in a conformal class. So you have the map to the sphere. It turns out that this map in this case is an isometric immersion. Right, so never mind the word branched for now. I will elaborate on that at some point in the second video. So we have this immersion. Again, it's just an isometric immersion to the sphere. It's good, but it's not quite special. Right, so let me explain it actually is special. So for that, let me just quickly give you a definition of harmonic maps of minimal surfaces. Again, this will be explained in more detail in video 3. But essentially, harmonic maps, minimal surfaces, they are generalizations of geodesics. Geodesics are both extreme of energy and length. In higher dimensions, those are two different things. Extrema of area called minimal isometric immersions. Extrema of energy are called harmonic maps, right? I'll just leave it like that. If you want more detail, go to video 3. And so it turns out that if your target manifold is a sphere with a standard round metric, and your map is such that its components, right? So here I understood it as a vector equation, right? So its components of the map phi are all eigenfunctions with the same eigenvalue, then automatically such phi is harmonic. Right? So it's a harmonic map right away. And moreover, if it's isometric map, then it's minimal, and lambda equals dimension of the M. Right? So that's why we scaled, because for surfaces this is 2, so lambda has to be equal to 2 for phi to be in isometry. Right, so the takeaway here is that the extremal metrics in conformal class correspond to harmonic maps, GSM, and extremal metrics in space of all metrics correspond to branched minimal immersions. Again, branched, I will elaborate on the word branched a little later. Right, and so this is fundamental to the whole theory, and it's why in the recent years this area just very popular in geometric analysis, is that it provides a connection between two unrelated topics, right? Seemingly unrelated. Maximization of eigenvalues and minimal surfaces. So it allows for fruitful exchange of ideas, right? So you can use ideas for minimal surfaces to prove bounds for eigenvalues, and you can use ideas from spectral theory to prove something for minimal surfaces and harmonic maps. Right, and one of such examples will be at the very last video, where this interconnection will play an important role. All right, so I'll leave you at this. We'll start next video with discussing those examples, right? So we know that those examples are maximal. So there has to be the corresponding map. So next time we'll look at the corresponding maps for all those 3 examples.